that substitution rule is convenient, very convenient, but integration by parts is important, very important in some sense. So here's why, exactly why. So f of x is a sine x, and to calculate this sine x, we use a calculator, right? So here it means sine 1 radian. We're going to go to calculator and hit that number, and this tells you one interesting way of calculating sine 1 without even using any measurement or anything like that. It's a fantastic idea, and that's what you show you importance. So let's say, so we start with a sine 1 minus sine 0. You write it like the sine 1 minus sine 0. Doesn't it look like some integration, right? fb minus fa. So can you write it like this is 1 to 0 to 1 of the derivative of this one. This is supposed to be antiderivative of something, right? So let me write it like this. Instead of what is the derivative of sine is a cosine, right? But I'm going to write it like this, f prime of t dt. Does that make sense? Antiderivative of f prime is, of course, f. So fb minus fb, fa. That's simple statement, correct? So you go like this. So we want sine 1, so we can write it as a sine 0. Sine 0 is easy to compute, relatively easier than sine 1. So it's plus 0 to 1 f prime t dt. Is that good? Now we do kind of integration by part in here, but there are many choices of doing this integration by part, but they came up with a clever choice of this invisible one to be integrated. Here's what makes difference in here. So that's going to be integration by parts. So if I insert invisible 1 in here, so they use a, I think they use a t. So that would be 1 minus, wait a second, let me think about it quick, number. So what would be the, wait a second, I don't get that. Let me think about it 1 second here. Oh, it's 1 minus, it's got it. So this is a bit strange integration, but they figured out this one, this little trick that makes a difference. So usual integration of 1 would be just the t, right? But they come up with the following, negative, actually t minus 1, with 1 minus negative. If I differentiate this one, what do you get? 1 came from that one here, so not that invisible. If I differentiate that one, I do get positive 1, right? Yeah, that's strange, but let me formulate it this way because it's without the way it's usually stated. So I'm applying the integration by parts. The if integral of 1, this is actually in simple form is a t minus 1. So rather than putting the integral t, we're playing with a t minus 1. That's the difference here. So the integral it would be minus 1 minus t and f prime of t. Does it look like a first bit of integration by part? That 1 is integrated here. Okay? Not just the t, but they're using t minus 1. So that it takes care of this 1 in here. That's a little trick that makes a big difference. And because of this negative, negative becomes a positive in integration by parts. And we have f. This one is differentiated this time. So isn't that just 1 minus t differentiated one more time, f double prime of t dt, integral from 0 to 1. Is that right? So that one repeated here, negative, negative become a positive, and that one is differentiated. Good? So let me write that down. And sine of 1 is a sine of 0, which is just a 0, but let me just keep it this form. And, well, I forgot to put 0 and 1 in here. So about that. 0 and 1. I'm going to further calculate and simplify there. If you plug in 1 in there, that's going to be just 0, right? 1 minus 1, that 1 came from the upper limit, so that's always going to be 1. If you plug in 0, that becomes positive. It becomes just f prime of t. F prime of 0, if you plug in 0 in there. F prime of 1 disappears because of this is 1, and that's the nice trick about that. This term isolated here doesn't have anything about f of 1 or f prime of 1, anything like that. So this one is just simply like this. 0 to 1, 1 minus t, f double prime of t. So what we're trying to do here is that if you repeatedly use integration by part, some weird formula shows up that helps us to compute the sine x, sine of 1 in elementary way. Although the idea behind it is sophisticated like this. So we're going to write that down. That was really f of 0, right? Sine of 0, f itself is a sine. That one here is f prime of 0, is that right? Prime of 0 and plus, that one is written 0 to 1, 1 minus t, f double prime of t, and dt. That's what we got so far. So we're going to integrate one more time of this one, and integration by parts. So we don't have much choices. We just have to integrate that one, 1 minus t, and differentiate that one, right? So we're going to do. So how's that going to look? So integral of that one. Anybody see the integral of that one? If you look at 1 minus t squared, and if you differentiate that, you definitely get 1 minus t to the first, right? But 2 shows up, and the derivative of 1 minus t, negative 1 shows up. So the constant that takes care of everything is, if you actually integrate 1 minus t, then it turns out this is the integral form. This elementary calculation, I just skipped it here. And f double prime of t, nothing happens to that. That's integration by part. From 0 to 1, definite integral. Now, because of this negative, it changed to positive again. There's 2 and 1/2 out there. And it's 1 minus t squared. This time, this is differentiated 3 times like this, right? And dt. And going from 0 to 1. So see what happened is 1 is plugged in here. F double prime of 1 will be a difficult quantity to calculate. Sine of 1. The whole thing is about unfolding the sine of 1. And this is still sine and cosine of 1. But because of 1 minus 1, it disappears. But when you plug in 0, that negative that becomes a positive is a 1/2. When you plug in 0, this whole thing is 1, and it's double prime of 0. It's like that, right? And then this keeps exactly the same thing. So let me write down sine of 1 one more time. Here's this f of 0, which is sine of 0. And f prime of 0, that's a cosine of 0. And then 1/2 of f double prime of 0. What's f double prime of 0? F is a sine, so cosine is a negative sign. Is that right? It's a negative sign, yeah. Then what we have is 1/2 and 0 to 1, 1 minus t squared f triple prime and t dt. That's how we get there. Miraculously, if you keep doing integrate that one, differentiate that one, integrate that one, and differentiate that one, they always keep this form. So I will skip the next calculation and write down, it seems like the pattern is clear. F of 0, f prime of 0, and 1/2, and second derivative. And what do you think is going to happen when you differentiate, integrate that one? What number shows up? When you integrate that one, it's going to be third power, right? And 1/3 will show up. So 1/3 shows up. And here, f triple prime. And then we have, and this number shows up exactly 2 times, 3 times, and 1 minus t to the third power, f differentiated 4 times. I hope you remember this notation, parenthesis notation. So you repeat exactly like that. If you look at this one, these are all easy to calculate. And if you believe this one is getting smaller and smaller, and there's an interesting thing going on. This is very, very small quantity as you do more and more, and this is something that we easily compute. So I'll do one more time, and then I'll give you an approximation. F of 0, f prime of 0, 1/2 second derivative 0, 2 times 3, third derivative 0, and what's going to be the next one? You integrate this one again, 1/4 shows up, right? So it's going to be 2 times a 3 times a 4 shows up, and the derivative is a fourth derivative 0 there. And the next term is that, what is that all together? 24, right? 24 from 0 to 1. And here is the fifth power, is that right? Third and the fourth power. I was wrong, fourth power. And fifth derivative dt dt. In there. All right? If we can convince that this is not too big, it's a fairly small quantity, then this is a good approximation to the quantity sine 1. So I'm going to go ahead and calculate this one in here. What is f of 0? The sine of 0, right? Sine of 0. What's sine of 0? It's a 0. This is a cosine of 0, right? What is cosine of 0? It's 1. What is this one is going to be this one is going to be cosine, it's going to be sine, right? Isn't that a negative sign? But negative sine of 0 is going to be 0 again. What about this one in here? It's a negative cosine, is that right? Differentiate again, negative cosine. So this one, negative cosine 0 picks up negative, so it's a negative 1, 2 times 3, and plus this one becomes positive sine again, right? So sine of 0 is a 0, is a 0. And plus, there is this term 24. It got large. Where did the 24 come from? It's 2 times 3 times 4, that number. So it came from 0 to 1, and 1 minus t to the fourth. And what is the fifth derivative? Is a cosine t. So it's a cosine t. I'm going to write that down. dt. Okay? Of course, all the difficult part went in there. Okay, I'm going to call the entire thing E. I'm going to estimate what E is. Not exact calculation. So E, absolute value of E is usually what they calculate. This is error term. If you use a numerical integral and the sage calculate the value, right? And right next to it, remember there was an error term? That's why we have to put this 0 parenthesis to pick a whatever the estimate they gave. And this is kind of that error term is going to give you an idea what this number is. So if it is absolute value, then this is absolute value of 1 over 24, that's 0 to 1, 1 minus t to the fourth, and cosine t dt. Is that right? Okay. No, not without using any information about this, what happened inside the integrand, although between 0 and 1, this is always a positive. So we're integrating Riemann sum of positive quantities, so absolute value means nothing here. But if it is changing the sign, and if I put, think about in terms of Riemann sum, I change all the quantities to positive quantity like that. If I put everything to a positive and then sum up, and there will be no cancellation. If they change the sign without absolute value, there possibly might be some cancellation, right? But if I change everything to positive, if you compare these two things, in general, this one is always a bigger. You add them all up and change the positive versus change the entire integrand, the little sum, to positive and add them all, then that's definitely bigger, right? So we have this inequality, and the cosine varies always in between where and where? 0 and 1, right? That always varies 0 and 1. So I can replace with the maximum possibility, 1. Then it's going to be 1 minus t raised to fourth power replaced by 1 with the absolute value rounded. Because if I replace with the maximum value, it's going to get bigger when it's replaced by maximum value dt. And now this is easy to integrate. So what is that? It's 1 over 24th. If you integrate that value, it turns out it's 1/5. Okay? So what is that? It's 120. Is that right? 120. That value right there is a difficult part, is less than 120. So we got this major value in here within the error margin of 120th. The sign of 1 is this number. What is this number? 1 minus 1/6. Is that right? So it's a 5/6, correct? And plus some error term. The error term behaves 120th. So let me get what that number is. 1 divided by 120, right? where is it? 1 divided by 120. There's a 0.0083. This is 0.0083. I got this number 5 divided by 6, and it's very close to sine 1, and is guaranteed that within that margin, 0.0083. All right. So if you go further and further to the right, and this 24 gets bigger and bigger, and this came from 2 times, 3 times, 4 times, 5 times, 6 times. If you do, several more times, and this is going to be the error margin, right? It's pretty good calculation you're going to go through after you do that. So I didn't go through triangle. I didn't measure anything, but I guarantee that this mechanism will tell you how the sine 1 is, to the arbitrary precision, how we can calculate, right? The error margin can be guaranteed something like this. If you do 4 more times, it's going to be like this. This is very, very small error, right? So this is the end of Calc 2. Calc 2 ends like this. But they have this exercise and put it in that section 7.2, and it's right here. It's really easy to show you the power of integration by parts, right? Kind of stripping off the value in a very different fashion using the integral idea. And you can calculate sine 1. You can calculate e, you can calculate root 2, the things that you've known. You can calculate pi, actually. You will see in the session 4, pi is written down as a sum of rational number in the fashion you definitely recognize. If you look at the decimal expansion, you have no idea what happens to, decimal expansion of pi, right? But if you use integration by parts, you can write down pi in a pattern. Take this rational number, you add this rational number, and if you do that, it approaches pi, and you understand the pattern. That's the power of integration by parts. It's kind of